In this lecture, we will introduce compilers.
We're now going to go back to our discussion with languages. Now, we mentioned before that these high-level languages really help the user understand the program. And they also vary greatly in structure and behavior, but they all share one feature. There's no computer in the world that has any idea what these instructions do. They just don't have a clue. Machines don't understand these high-level languages. There are no Java computers, there are no C++ processors that can directly execute programs that are written in high-level languages. And just like assembly languages, high-level languages have to be translated into machine language prior to execution. We have to have this translation being done. And in this case, it's actually done by a special piece of system software, which is called a compiler. So the compiler will take care of this translation process for us. The compilers for these languages are very complex programs. They contain tens of thousands of lines of code and may require dozens or even hundreds of person years to actually complete. It takes a while to put together a compiler. And unlike the assemblers that we've talked about before, these translators are not very easy to design or even implement. So I want to make a clear distinction between assemblers and compilers. There is a difference in the complexity between the two. Why is a compiler more complex than an assembler? Well, with assembly language and machine languages, they're very related to each other. In fact, there's a one-to-one relationship. So whenever we translate an assembly language instruction, that actually gets translated to exactly one machine language instruction. So the translation is really a replacement process in which the assembler would look up a symbolic value in a table. So this could be the opcode table, this could be the symbol table, and then it just replaces the statement with a numeric equivalent. So for example, if we have something like load x, well, we're going to look up the load operation in the opcode table. We're going to look up the x in the symbol table, and then we get our machine level instruction, which is a bunch of zeros and ones. Now, with high-level languages, on the other hand, we don't have this one-to-one relationship. It's more of a one-to-many relationship. So whenever a compiler translates a single high-level instruction, it's actually being translated into many machine language or even several assembly language instructions. So just to give an example here, let's say I have something like A equals B plus C minus D. That's a single statement in high-level languages. But when we translate it, it actually becomes several assembly level or machine level instructions. So this would have to be load B and then add C and then subtract D and then store A. So here, one high-level instruction turns into 4 assembly language instructions. To determine which machine language instructions must be generated, a compiler simply just can't look up a name in a table. Instead, it must do a thorough linguistic analysis of the structure or the syntax and the meaning or the semantics of each high-level language statement. And this is far more difficult than just a simple table lookup. In fact, building a compiler for a modern high-level programming language can be one of the most difficult system software projects. So when performing a translation, a compiler has 2 distinct goals. The first one is correctness. So a machine language code produced by the compiler must do exactly what the high-level language statement describes and nothing else. So if the translation is wrong, that doesn't do us any good. What's the point of the translation if it's not even correct? So we have to make sure that we are translating the high-level language to the machine language correctly. In addition to correctness, the second goal is that the code must produce reasonably efficient and concise code. So, even though memory costs have come down and processors are a lot faster, programmers won't accept gross inefficiencies in either the execution speed or the size of the compiled program. They might not care whether the compiler eliminates every wasted nanosecond or every unnecessary memory cell, but they do want it to produce reasonably fast and efficient machine language code. So, it may be correct, but it doesn't do us much good if it's going to run a lot slower in the translated language. So we want to make sure that it is at least reasonably efficient in terms of the speed and the size of the program. The compilation process is actually broken up into 4 different phases. The first phase is what we call the lexical analysis. So the compiler is going to examine the individual characters in the source program and group them together into syntactical units, which we call tokens. And these tokens will be analyzed in succeeding stages. So this operation is analogous to grouping letters in a word prior to analyzing the text. The second phase is parsing. So what we do here is the sequence of tokens that are formed by the scanner is checked to see whether it is syntactically correct according to the rules of the programming language. This phase is roughly equivalent to checking whether the words in the text form grammatically correct sentences. The next phase is the semantic analysis and code generation. Sometimes these phases are broken up into 2 different steps, but right now we're just going to combine them into one. So here, if the high-level language statement is structurally correct, then the compiler is going to analyze the meaning and generate the proper sequence of machine language instructions to carry out these actions. And then the last phase is code optimization. So the compiler is going to take the generated code and see whether it can be made more efficient. So this may involve making it run faster or maybe have it occupy less space. Let's start by discussing the lexical analysis phase in more detail. The program that performs the lexical analysis is called a lexical analyzer, or more commonly known as a scanner. And it's the job of the scanner to group the input characters into units called tokens. And these tokens are syntactical units that are treated as single, indivisible entities for the purpose of translation. Let's take a look at an example. Let's suppose we have the following assignment statement, something like A equals B plus 319 minus delta, then we end with a semicolon. Now you probably see the assignment statement containing some symbols such as A, B, and delta, the number 319, and even some operators like the equal sign, plus, minus, even the semicolon. But there's actually a lot more in here than we think. And that's because when we're scanning this, we have to consider all the blank spaces, tabs, all that needs to be considered as well. So if we were to actually process all of the symbols in here into tokens, we would get something like this. We would get a tab first, and then the A, and then a blank space, and then an equal sign, another blank space, the symbol B, another blank space, the plus sign, another blank, a 3, a 1, and a 9, another blank, a minus sign, another blank, and then all the letters D, E, L, T, A, and then a semicolon. So it's the task of the scanner to discard the non-essential or the non-needed characters, such as blanks and tabs, and then it grouped the remaining characters into high-level syntactical units, such as symbols, numbers, and operators. So basically, we can take out all of the tabs and all of the blank spaces, and this is what we would get as our set of updated tokens. So we would have the A, the equal sign, the B, the plus, the 319, the minus sign, the delta, and the semicolon. So now our compiler no longer has to deal with the individual characters, but instead it can actually work at the levels of symbols, numbers, and operators. So in addition to building tokens, a scanner needs to classify the tokens by their type. So here we're checking, is it a symbol? Is it a number? Is it some type of assignment operator, an equal sign? Is it addition, subtraction? What type of operator do we have here? So, I mean, modern high-level languages like C++, Java, or Python may have 50 or more different token types. We're not going to go over all those token types. We just don't have time for that. But we're just going to look at some simple examples here. But the whole point is that each token is going to have a unique classification number. So when we scan the statement, then we can assign each token the respective type classification number. So like, for example, we could assign the number 1 to all legal symbols, such as A, B, and delta. Similarly, we can have all unsigned numbers, regardless of what the value is, be assigned classification 2. And the reason all symbols and all numbers can be grouped into single classifications is that the grammatical correctness of a statement depends only on whether a legal symbol or a legal number appears in a given location. It doesn't depend on exactly which symbol or which number is actually used. And we can continue this on with other symbols as well. So like the operators equals could be a 3, plus sign could be a 4, minus would be a 5, semicolon would be a 6. But our output when we do this is going to be the list of all the tokens and the classification number for each token. So we get this pair between the token and the classification number for that token. So if we use our earlier example of A equals B plus 319 minus delta semicolon, we would get something kind of like this. It might vary depending on which book you're looking at, but we would have the pair A with classification 1, equal sign with classification 3, B with classification 1, the plus sign with classification 4, 319 with the classification 2, minus sign with classification 5, delta with classification 1, and semicolon with classification 6. The whole point here is not only we know what the token is, but we also know the type associated with each token. And this is going to be needed for the other phases of the compiler process. Now, regardless of which programming language we're analyzing, every scanner performs virtually the same set of operations. So first, it discards blanks and other non-essential characters and looks for the beginning of a token. It will then, when it finds the beginning of the tokens, it'll put the characters together until it detects the end of the token, at which point it classifies the token and begins looking for the next one. So this algorithm is going to work properly regardless of what the token looks like. So what we're doing here is we're getting rid of all the blanks. We're going to try to find the beginning of a token, and it puts the characters together until it detects the end of the token. So that's all we're doing as far as trying to figure out the tokens that are part of that particular language.